Okay, so you see, let me tell you, let me recall the notation that I used. Okay, this is just to make sure that I don't mess up the notation. So you know, we have this situation that so if you recall, what we had was we had so you had x and y varieties and you had small x in capital X, small y in capital Y, and you had psi from the local ring of capital X at small x to the local ring of capital Y at small y. You had an isomorphism, K algebra isomorphism. Okay, we had this, and then what we did was we wanted to show that if you have two varieties and there are points where the local rings are isomorphic, we wanted to show that there are open neighborhoods surrounding those points which are actually isomorphic as varieties. Okay, so in other words, there is an open set. We wanted to find an open set containing x and an open set containing y and an isomorphism between these two open sets. Okay, and the point is that that isomorphism at local rings will induce this isomorphism. Okay, that is what we wanted to show. So what we did was, so this was given to us. Okay, and what we did was of course, because any variety is covered by finitely many open sets, each of which is isomorphic to an affine variety, what we did was we took an affine variety, we took an open set containing small x which is an affine variety and an open set containing small y which is also an affine variety, and therefore you know, we had the diagram like this. We had x here, we had x1 inside x which is an affine open, and we had small x belonging here, then we had capital Y and we had this capital Y1 which is an affine open subvariety which contains the point small y. Okay, and if you look at it in terms of this is a geometric part. If you look at it commutative algebraically, you got Ox here, that corresponds to the regular functions on x. You have Oy here, and then you have this restriction of regular functions on x to regular functions on x1, so you have Ox1, but that is the same as Ax1. Okay, and of course this is an inclusion, because that's because if a regular function is 0 on a proper open set which is non-empty, then it is 0 everywhere, okay. And another way of saying it is of course that if two regular functions coincide on a non-empty open set, they coincide everywhere. That is the reason why this map is injective. It is a and of course this map corresponds to restriction of regular functions to the open set x1, and similarly you have an inclusion of this with OY1, and OY1 is the same as AY1 because and OX1 is the same as AX1. This is because x1 and y1 are affine varieties. For affine varieties the ring of regular functions is the same as the affine coordinate ring, right. And then of course then we go all the way to the point by going to the local ring at that point, and the local ring will not change if you go to an open set, if you go to a smaller open set which contains the point. So this is the same as the local ring of x considered as a point of the open subvariety x1, right. And similarly here we have the local ring of capital Y at small y, which is also the local ring of small y at as a point of capital Y1, alright. And we know that you see we had given names for these rings. We call this ring as A, we call this ring as B, okay. And the point small x as a point of x1 will correspond uniquely to a maximal ideal of A, and we call that maximal ideal as M, and the point y small y will be will correspond uniquely to a maximal ideal of B, we call that as N or neta. And so you know x so this local ring becomes it can be identified with A localized at M, okay. This is the expression for a local ring. At a point you take the if you have a point of an affine variety, then the local ring at that point is given by simply taking the affine coordinate ring, which is the same as the ring of regular functions, and then localizing at the maximal ideal that corresponds to that point. And similarly this is identified with B localized at N, okay, where M corresponds to so this x corresponds to M in the maximal spectrum of A, where A is A of x1, and y corresponds to N, which is in the maximal spectrum, which is a set of maximal ideals of B, where B is of course the affine coordinate ring of y1, right. And then of course we have then all this is happening inside the respective quotient fields. All these things have the same quotient field. I mean this the quotient field of AM is the same as the quotient field of this, is the same as quotient field of this, which is the quotient field of A, and that is also equal to the function field of x. So what you must understand is that this is happening inside quotient field of A, which is the same as quotient field of A sub M. This is also equal to function field of this is also equal to quotient field of that it's also equal to the function field of x. The field of rational functions of x is also equal to the field of rational functions of x1. The field of rational functions does not change if you go to an open set, okay. And similarly here I am going to get this is all this is going to sit inside. By the way I should also tell you that when you go from the ring to its localization, if the ring is an integral domain, this is also an injective map, okay. From a domain to its local ring to any of its localizations, the natural map given by localization is an injective map, because the source is a domain. When you localize a domain you get a bigger subring of the quotient field of the domain, okay. So similarly B is a domain, and if you localize B at the maximal ideal neta, you are going to get a bigger subring of the quotient field of B, this Q of B, that is the same as the quotient field of any localization. In this case it is also the quotient field of the field which is a field of fractions of the local ring, and this is also equal to the function field of y1, so the function field of y, they are all the same, okay. And the point is that it's at this level, so I have this isomorphism here, so I have this psi here, this psi is given to me, alright. Somehow I have to use this psi to produce an isomorphism between an open subset of x1 containing the point x and with an open subset of y1 containing the point y. So I have to somehow cook up those open sets, okay. So so what we had done is that we had assumed that see your A, which is a affine coordinate ring of x1, if I look at the notation, A was k s1 etc sn divided by the ideal of x1. This corresponds to putting because x1 is an affine variety, okay. x1 sits inside some a n, okay, and if you take the affine coordinate ring of an as a polynomial ring in the variables s1 through sn, okay, then the affine coordinate ring of x1, which is ax1, which we call as a, is going to be just this polynomial ring divided by the ideal of x1, okay, where of course here when I say x1 is being considered in an, here it is being considered as an irreducible closed subset of an, okay, which identifies it as an affine variety, right. And then we also have similarly B is also a polynomial ring in m variables divided by the ideal of y1, where similarly what we are doing is that we are thinking, since y1 is an affine open subset of y, it means that y1 is an open subset of capital Y, but it is also abstractly isomorphic to an affine variety. Therefore you can identify it, you can embed it as an irreducible closed subset of am, and on this am, if you take the t's t1 through tm to be the coordinate functions, then the affine coordinate ring of that am is this polynomial ring in the t1 through tm, and if you go modulo the ideal of y1, you will get the affine coordinate ring of y1, right. And now in terms of these rings, we have this inclusion of a into am, and this is b into bn, okay, and of course am is sitting inside the quotient field of a, and bn is sitting inside the quotient field of b, and of course my the isomorphism that is given to me is between am and bn, okay. This is the K algebra isomorphism that is given to me. Of course all ring homomorphisms we are considering are all K algebra homomorphisms, okay, and I mean essentially they are all as far as the same variety is concerned, they all correspond to going to I mean going from here to here corresponds to taking germs of regular functions, and then going from here all the way to the quotient field is trying to look at an equivalence class, trying to look at a regular function as a rational function, okay, and across from one side to the other we always think of ring homomorphisms as coming because of morphisms by a pullback of regular functions, but the point here is that we have to construct the morphism, we have to construct an isomorphism between an open subset of x1 and an open subset of y1, okay. So so what we did was if you remember, so we had made all these assumptions. We had put psi of si bar by 1 is equal to fi bar by gi bar, okay, the SI's are polynomials here, and the SI bars live in this quotient, and you are considering them as because this is a sub of this, okay, this is a subring of this, so you are considering them as elements here, okay. So SI bar by 1 is an element here, and then I apply psi, I get a quotient, I get an element here, a quotient where GI bar is not in the where GI bar is certainly not in the maximal ideal n, okay, and then this has to be probably psi inverse. 1 by GI bar lives here, this has to be psi inverse, okay, and similarly I do for psi inverse, I take the image of the coordinate, the generating coordinate variables, the generating functions, the tj's, and so this is what I have. Now what I want you to check is that see, if you take this set, if you take this localization A localized at product of Gj bar, product of Ai bar Bi bar, product of psi inverse of Bj bar, okay, and you see and you take this localization, okay, and then you take this localization on as far as so this is you know A is going to sit inside this localization, and B is going to sit inside this localization, and in this localization you take product of capital G I bar to product of Aj bar Bj bar, and I think you will also have to take psi of Bi bar, product of psi of capital Bi bar, okay. So now the fact is that if you of course these localizations will sit inside Am and here inside Bn, okay, these localizations will sit here, and what you can check is that the way we have defined psi and psi inverse, you will get an isomorphism like this, okay, you will get an isomorphism like this, and that is just because of the universal property of localization. You will get a map like this, and you will get a map in the reverse direction, okay, you will get an isomorphism between these two, alright, and such that this, so you will get this map here, which I would like to call by some name, maybe I will call it as I do not know what I had so it was probably phi. So you know you have you have this map yeah, so let me put the arrow in this direction and call this as phi inverse, okay, you will get a map like this, K-algebra isomorphism phi inverse. Phi inverse will just come because of the universal property of localization and the way, because of the way in which these are defined, and what will happen is that this phi inverse, you know, if you take this phi inverse, then I will also get phi inverse what this phi inverse will do is that it will also induce an isomorphism here, okay, and this isomorphism will be the same as the isomorphism psi you started with. So you will get something like this, you will get this, okay. You see everything was constructed using psi, alright, therefore the point about inverting all these elements is to go to a proper I mean it is to go to a proper open subset, to go to an open subset of the affine variety with coordinate ring A, okay, and the same way inverting all these things here is the point is to go to an affine open subset of the variety y1 whose coordinate ring is B, okay. So this this is the affine coordinate ring of an affine open subset of y1, and this is the affine coordinate ring of an affine open subset of x1, okay, and this isomorphism of affine coordinate rings gives an isomorphism between open subsets. So you therefore, so hence you will get, hence we get, you see you have x, and inside you have x1, and inside x1 you have this u, okay, and where what is this u? This u has affine coordinate ring given by this whole expression, so this is AU, okay, and similarly, so this is affine open, and this is also again affine open, okay, and similarly at for y you have y1 which is affine open, and here if we call it as V, that will also be another affine open, and what you will get is that you will get a morphism. So I think so notation wise, let me do something. I say that I will get an isomorphism phi, okay, such that if you take the isomorphism that is induced by pullback of regular functions, because an isomorphism between affine varieties corresponds to an isomorphism between their affine coordinate rings, which is a K algebra isomorphism. So this will induce a phi hash, so let me change this to phi hash, okay, and then the direction is correct, so I will call this as phi, let me call simply this as phi hash, okay, and then this isomorphism will take the point x to the point small x to the point small y, so it will induce an isomorphism of the local ring of y with the local ring of x, and that is exactly this. So that is just phi upper hash at y, and mind you, this is identified with OVY, okay, which is of course the same as O y1y, and is also the same as OYY, right, and this is identified with O UX, okay, and y is of course phi x, okay. So this phi hash at y, this is isomorphism at the level of local rings, this is the original psi that you started with, okay. So the moral of the story is, if you start with an isomorphism of a K algebra isomorphism between the local rings at points of two varieties, then those two varieties are birational. That means there are open subsets on each which are isomorphic to one another, okay, and I told you that the property of two varieties being isomorphic on open subsets is called birationality, okay, and so all you are saying is that if the local rings at 2 points of two varieties are isomorphic, then the two varieties are birational. So this is just to tell you that the local ring carries a lot of information, okay, it carries a lot of global information also, reasonably so, global information in the sense that it does not carry information about the whole variety, but it certainly carries information about an open set containing the given point where you are considering the local ring, but that open set is of course dense open set, it is a non-empty open set, it is irreducible and dense, because of the Zariski topology open sets are all huge, okay, therefore the local ring also contains information over a huge open set, okay. So that is so you know that so as a matter of fact you must also notice that the dimension of the local ring is the same as the dimension of the variety. So the moment the local rings at two given points of two varieties are isomorphic, it means that first of all it means that the varieties are having the same dimension, okay. So you can't, this will not happen if the varieties do not have the same dimension, okay. If the varieties are of different dimension, then you cannot find an isomorphism. Even I mean you cannot find an isomorphism between local rings from a point of one variety to a point of the other variety. Okay, therefore the first thing you should notice is that once you have an isomorphism of local rings, it already tells you that the two varieties are having the same dimension, but the story is more. The fact is that the isomorphism of local rings actually makes them birational. Okay, so that is to say about the power of local rings. But then I also want to tell you about in connection with this about the power of function fields. Okay, so the next result that I am going to talk about is about the fact that if you have two varieties such that their function fields are isomorphic as K algebras, okay, then also they are birational. Okay, so isomorphism of function fields of two varieties is also it also has the same effect as having an isomorphism of local rings. Okay, so let me give this notebook back to you. So let me make so here is a theorem. So this is kind of because it's connected with this, I'm continuing with this. If two varieties, so this tells you about the importance of function fields. Okay, if two varieties have isomorphic function fields, then they are birational, and conversely. Okay, two varieties X and Y with isomorphic as K algebras function fields are birational. Okay, so this is now I am for a moment I'm trying to tell you about the importance of function fields, right. So the function field of a variety is an invariant in the sense that it will only change up to isomorphism if you change the variety up to isomorphism. Okay, so of course if two varieties are birational, okay, then there is an isomorphism on open sets. Okay, and this isomorphism on open sets will lead to an isomorphism of the function fields. Okay, and the function field will not change if you go to an open set. Okay, so if two varieties are birational, then certainly their function fields are isomorphic, that is obvious. Okay, but what is not obvious is the other way around. If you just say that the field of rational functions on one variety is isomorphic as a K algebra, okay, to the field of rational functions on another variety, that is good enough to saying that that is as good enough as saying that the varieties are themselves isomorphic on open subsets, namely that they are birational. Okay, so the proof for this also runs in more or less in the same I mean the ideas are nearly the same as in this proof. Okay, so what you do is, see you have so I have X, I have Y varieties, alright, and I have Kx and I have Ky, they are the function fields, and I am given an isomorphism, let me call this a zeta. Okay, this is a K algebra isomorphism. So I have K algebra isomorphism between the function fields of two varieties. Okay, and what I want to say is that just as in this case when you have an isomorphism of local rings, as you are able to cook up two open sets where they are isomorphic, you can also cook up open sets here and here where the two varieties are isomorphic. okay. Just an isomorphism at the function field level is enough, okay. And how do you do that? So again what we will do is we will go to so just as we did there, we went to affine open sets, okay, which is which helps us to translate everything into commutative algebra, okay. So we can do the same thing here. We can assume that x1 is an affine open in x, and y1 is an affine open in y. And well, if you go to an affine open, of course whenever I say open set, it is a non-empty open set. I am not worried about the empty open set, okay. So if you go to an affine open set, then what happens is the function field does not change, okay, the function field does not change. So this is the same as k of x1 and this is the same as k of y1, okay. So it is enough to show that x1 and y1 are birational, okay, because that will mean that x and y are also birational just because x1 is just an open subset of x and y1 is an open subset of y. So again I follow the same I follow with the same notation. So what I do is I think of x1 as sitting inside an, okay, and I think of y1 as sitting inside am, alright, and I take on an I take the coordinates to be s1 through sn, on am I take the coordinates to be t1 through tm, okay, and I write a to be the affine coordinate ring of x1, b to be the affine coordinate ring of y1, okay. I use the same notations, but the only thing that is missing is I don't have these 2 points and the local rings and an isomorphism between local rings. I don't have that, but I have the isomorphism here. I have the isomorphism at the quotient field level, because after all the quotient field of the affine coordinate ring of a variety is the same as the function field of the variety. So what I have now is, as before what we get the following diagram. You get a diagram similar to this, only that you don't get this, okay. This is not given to you. There is no point here going to a point there such that the local rings are isomorphic. There is only an isomorphism between the quotient field of A and the quotient field of B. So what happens, we get this diagram. So let me write it down here. So A is the affine coordinate ring of x1, and what I have done is as in that case I have embedded x1 as an irreducible closed subset of an, so that its affine coordinate ring becomes the affine coordinate ring of that an, which is the polynomial ring in the coordinates s1 through sn modulo the ideal of x1 in the affine space, okay. And I have on this side I have y1 also embedded as an irreducible closed subset of am, and here again I will get if I take the coordinates on am to be t1 through tm, then if I take k of t1 through tm, this is going to be the coordinate ring of the affine space am, and then if I go modulo the ideal of y1, I end up with b, which is the affine coordinate ring of y1, okay. And then what I now have is, well, this is sitting inside the quotient field of A, but the quotient field of A is just the function field of x1, and that is the same as the function field of x, and similarly this is sitting inside the quotient field of B, which is the function field of y1, and which is also the same as the function field of y. And now I have this isomorphism zeta, which is an isomorphism between these two function fields, okay. Now now I have to play nearly the same game as I did here, and well, in fact the truth is that somehow in a way if I had proved this statement first, okay, then that statement would have been easier to prove, because if I had given you this statement first, then if you go back to this situation, this isomorphism between local rings will induce an isomorphism between the quotient fields, and once I have isomorphism between the quotient fields, if I grant that I have already proved that it is birational, I am already done. So in a way this could have been deduced from here, but then there is no harm in doing it like this because you learn some techniques, okay. So basically what we do in this situation is the following. So you look at all these SIs, okay, which are in the polynomial ring, their images in A are the SI bars, okay, and they are all elements of this quotient field, and you apply zeta to them, okay. So what will happen is that you get all these each of these SI bars going to I mean you are thinking of SI bar as SI bar by 1, that is the way you think of elements of the domain as elements of the quotient field, okay, and you apply zeta to this. So I will get zeta of SI bar by 1, alright, and the point is that all these what are these zeta SI bars by 1? Well, they are rational functions on y1, they are rational functions on y1, and what's a so you should remember that k y1 is rational functions on y1 up to an equivalence, okay. So rational function is given by a regular function on an open set, and two such pairs consisting of a regular function and an open set on which it is defined are said to be equivalent if in the intersection of those two open sets the corresponding regular functions coincide, okay, and mind you any two non-empty open sets will always intersect because of irreducibility, okay. So any rational function here is a regular function on an open set. So each psi zeta I bar by 1 is regular on some open set, it is a regular function on some open set, and there are only n of them, okay. So if you take the intersection of all those open sets, then these fellows will become regular functions on that common open set, okay. So so let me write that this is regular on U, let me call this as these open sets Vi open inside y1, okay, these are all regular there, and similarly I can do it the other way around. So what I can do is I can also look at the t's, okay, the tj's are all coordinate functions here, and their images in B will be the tj bars, and then you take their images here the quotient field, then followed by zeta inverse, okay, and I am going to get rational functions on this side, okay. So the same argument applies. So if I take the tj bar divided by 1, and then if I apply zeta inverse, mind you, then I'll end up with the zeta inverse of tj bar by 1, and these fellows are going to be regular functions on ui's, where ui's are open subsets of x1, okay. So these are going to be regular functions on ui which are open in x1, okay. So I'm going to end up like this. Now you see if you look at that carefully, so let me rub this. So what you do is you do the following thing. So this zeta of si bar by 1 is a regular function on Vi for each I equal to 1 to n, okay. Now you take the intersection of all those Vi's, okay, put V equal to intersection, or V is equal to intersection I equal to 1 to n Vi, okay, put this, then you see then the zeta of S1 bar by 1 and so on, zeta of Sn bar by 1, they are all in O V, okay, they are all regular functions on V, alright, because each one is regular on Vi and all of them put together is are going to be regular on V, alright. So you know the point is that you see we use this fact here. So if you recall there is a canonical bijection between the morphisms of varieties from any variety, if I call it as so I am short of notation, so let me use some script notation, I am short of symbols, so let me use some script notation. You take any variety X and you take an affine variety Y, okay, and if you look at the set of morphisms of varieties from script X to script Y, alright, script X to script Y, then this is in a natural bijection with the set of all homomorphisms of K algebras from AY to OX, and mind you AY is the same as OY because Y is affine, okay. See, we have already seen this, we have seen this bijection, the set of all morphisms from a variety into an affine variety is in bijective correspondence with the set of all K algebra homomorphisms from the affine coordinate ring of the target affine variety to the regular functions on the source variety, okay. Now you see what you do with these guys, okay, what you do with these guys is that I can use this to define, I can use these regular functions, n regular functions, to define a morphism from V into x1, okay. So what you do is, you see what you do is the following, I mean it is exactly if you go back and look at it, that is how we established this bijection, okay. So what you do is, you see you have see zeta restricted to A will actually go from A into zeta of A, which is a sub of OV, okay. You see zeta, if you see this zeta is from the quotient field of A to the quotient field of B, alright, and what is any element of A? Any element of A is a polynomial in the SI bars, okay. Any element, the SIs generate the polynomial ring of affine space, and their images will generate, the SI bars will generate A. Any element of capital A is actually can be thought of as a polynomial in the SI bars, okay, and therefore but all the SI bars, their images under zeta are all lying they are all landing in the K algebra OV, they are all landing in the K algebra OV, and therefore you see zeta will land inside OV, the image of zeta will land inside OV, alright, and as a result you see you get a K algebra homomorphism from A, which is A of x1 to OV. If you apply this bijection, this will correspond to a morphism of varieties from V to V to x1, okay, alright. So you know in this you apply with script x equal to V and script y equal to x1, okay, and you will get a morphism from V to x1. So by this result, this gives rise to a morphism of varieties from V to x1, okay, you get a morphism like this. And in fact, you know, it's even easy to write what that morphism is. It's even easy to write what that morphism is. The morphism is, see, after all, this V is see this V this V is an open subset of y1, and y1 is V is an open subset of y1. Y1 is sitting in affine space, so you know any point of V is given by m coordinates, okay, and you know you just take this point of V with m coordinates mu1 etc mu m, and you know what you will have to send it to, you will have to just send it to you know these are all regular functions on V, okay, these are regular functions on V, alright, and therefore they are given by quotients of polynomials in m variables on V, and you substitute for those m variables these values, okay. So that will give you an n tuple, and that n tuple will precisely be an n tuple of a n, it will land inside x1, okay. So if you call this as mu, okay, then this is just the map psi s1 bar by 1 of mu and so on, sorry, zeta s1 bar by 1 acting on I mean evaluated at mu and so on up to zeta Sn bar by 1 evaluated at mu. So you will get this n tuple, and this n tuple will be a point of n, in fact it will be a point of x1. That is how this bijection was established. If you go back to that lecture and try to recall, okay. So you get this morphism like this, okay, and you know if you call this so you know if you call this morphism as again let me use some notation, so now let me use so let me use psi here or let me use some other notation, so I'll use capital psi, okay, I'll use a block psi like that. So I have a morphism like this, right, and what is the meaning that this comes from this? It means that this is actually psi hash, okay, the map from here to here is just neta going to neta hash, because you know given a morphism of varieties you have the morphism at the regular functions level given by pullback of regular functions, okay, and what does it mean to say that I started with zeta restricted to a here and I ended up with this psi there? It means that this psi is zeta sorry, I started with a zeta restricted to a here and I got a psi here, it means that psi hash is that zeta, okay. So this zeta restricted to a is psi hash, alright, and moreover and this psi, you know what you must remember is that this psi induces psi hash is zeta, and mind you this zeta is part of an isomorphism at the quotient field level. This zeta from A to OV, if I go to the quotient field, okay, if I if I go to the quotient field level, it's an isomorphism. Zeta is an isomorphism of the quotient field level. That's something that you should not forget. All right. But anyway, you know, you can. So what we have done is, you know, if you look at the so let me rub this diagram lest it cause any confusion. So you know, the situation is now that what we have done is we have this x and we have this x1 which is affine open inside x, and well of course we embedded x1 inside affine space, but that is not important now. And then there is y1 here which is also affine open in y, and you see what I have done is I have got this V which is an open set in y1, and I have got a morphism like this. I have got a morphism like this, alright, and in the same, and for that I use the fact that all the zeta, si bar, they are all regular functions on this open set. Now I play the same game with zeta inverse of the tj bars, okay. So so similarly, if we put u equal to intersection I equal to 1 to j equal to 1 to m of uj, okay, then zeta inverse of t1 bar by 1 etc. up to zeta inverse of t m bar by 1, they are all going to be in OU, okay, where u is an open subset of x1, okay, and therefore if you take zeta inverse and restrict it to B, it is going to give you a map from B to OU, okay, and so I should say from B to zeta B, which is sitting inside OU. Mind you, this is an isomorphism, this is also an isomorphism because they are images under an injective ring K algebra homomorphism, okay. So zeta B is so zeta inverse B goes into OU, alright, and so you know, again by this yoga what will happen is that you are going to get a morphism of varieties from u to y1 given by some, let me call it as phi, capital Phi, like this, okay, such that well when you take this morphism and you take the pullback by regular functions, it gives you get phi hash, and this phi hash is actually equal to zeta inverse, alright. So this means that, you know, we have got one like this. So you have u open inside x1, and you have got a so if this is psi, then this is phi, okay. So u is here, I have used sub of this, so I have psi inverse of u. This is an open subset of this, okay, and then here I take phi inverse of C inverse of u, that here is an open subset, okay, and the fact is that phi will carry this into this and psi will carry this into this. The only thing that you will have to worry about is that the image of psi has to intersect u, okay, that's an important thing, because if the image of psi does not intersect u, then psi inverse u will become empty, alright, and similarly the image of phi should intersect psi inverse u, okay, and so these non-emptiness statements come because both psi and phi at the at the pullback of regular functions level they induce in fact injective maps, okay, and it is this injectivity that ensures that first that if you take u will intersect the image of psi, and that similarly psi inverse u will intersect the image of phi, okay, that is because of the injectivity of that follows from the way we have constructed them, right, and therefore you get this you get these maps and they will be inverses to each other. So the fact that you are using is that, you know, if you have two open sets and you have if you have two open sets, I mean if you have two varieties and you have two morphisms going in opposite directions such that, you know, the composite morphisms, so phi followed by c here and then psi followed by phi there, if they induce identity at the quotient field level, okay, if they induce identity at the quotient, if they induce the identity map at the quotient field level, identity of the quotient field, then they have to be inverse isomorphisms, okay. So, you know, if you go to the quotient field level, psi followed by phi is just going to be applying you know, this psi is going to induce you see this psi induces zeta at the quotient field level, phi induces zeta inverse at the quotient field level. So, you know, psi composition phi and phi composition psi, they will induce identity maps at the quotient field level if you have two morphisms, alright, which induce upon composition identity at the quotient field level, then those morphisms have to be inverses of each other, okay. So so that will tell you that you have so this gives open subsets of x1 and y1 which are isomorphic as varieties. What I wanted to remark is that you know, this when we, the way we got the isomorphism, the birationality in the case of isomorphisms of local rings, so the same thing will also work in this case, okay. So what you can do is that you can do something like this, okay, which was in the local ring case, right. So in fact you can get these things more explicitly by doing like this, okay. So, you know, so if I rub this off and try to write that out explicitly, okay, so you just have to take see, if you take zeta of Si bar by 1, this is an element here in the quotient field of B, so it's a fraction, so it is some Fi bar by Gi bar, okay, and then so, you know, and then if you take if you apply zeta inverse to 1 by Gi bar, alright, I will get some AI, I will get yeah, I will get an AI bar by Bi bar, okay. So 1 by so if I take zeta of Si bar by 1, I will get Fi bar by Gi bar, where Fi bar and Gi bar are, you know, polynomials in the T bars, okay. They are elements of B, and because this is after all the field of fractions of B, every element here looks like a quotient of elements of B, okay. And if I take the 1 by Gi bar, okay, which also makes sense in the quotient field of B, okay, and I apply zeta inverse, I will again get Ai bar by Bi bar, alright. And zeta inverse of if I apply zeta inverse to Tj bar by 1, I will end up with some capital Ai bar by Bi bar, I mean Aj bar by Bj bar, where Aj, capital Aj and capital Bj are polynomials here, okay, in the S's, right. And if I take if I apply zeta to 1 by Bj bar, okay, then that is going to go to some small Fj bar by small Gj bar, okay. And now what one has to do is that so whenever I have applied zeta, I am on the side of the B, I am working with the T bars, and whenever I have applied zeta inverse, I am working with the S bars, okay. So these two are connected with the T bars and these two are connected with the S bars.